today we're going to do graph search algorithms. All right? So you should all, and again, I'm going to assume you know nothing, even though you probably know some things. But if, if you're not following what's going on, ask questions. If you have some thought about what we're not currently talking about, save your questions for a pause. So what is a graph? It's a bunch of nodes and edges, and the edges could be directed or undirected, right? And I heard it once said that every problem in computer science can be expressed as a graph theory problem. I think that's an exaggeration, but it's certainly useful, right? So we're going to start with graph search, right, from a single source, right? So we're having a graph and we have a single source node, and we want to see where can we go, right? So imagine you're Mr. Google, and you want to reach every page that, 2 pages are linked. If you click on it, you get them, and you want to search out, right? So you find every node that is reachable from S, right? So how we're going to do it, I'm big on loop invariance, right? So I'm stating, okay, we've flown in from Mars, meaning all we know is the loop invariant. We know that U is connected by a path to S. And then what do? We kind of look out for the edges coming out of U, and we say, oh, look there's an edge to V. And so what do we now know about V? There's a path to V, right? V is reachable. How do you get to it? Well, you go to U, and then you go to V. Right? Everybody good with that? And so we're going to build up sets of reachable nodes. So S is reachable from S, and then those are reachable, and those are reachable, and those are reachable, right? The danger, what's the danger is that you might cycle forever. So how do we avoid cycling forever? Yeah, think about if those of you who know Hansel and Gretel, they drop breadcrumbs as they go along so that they know their path, right? So we don't want to keep track of that. So how do we avoid cycling? It's just that we said we keep track of where we've been. All right? So we first search out there, and now we know that A and B and G and B, whatever those letters are, right? Those, and then we search out from there, and we search out from D. Right here, we're searching out from S, and then we search out from A, and then we search out from D, right? And we want to think, what do we know about these various nodes? All right, so we found E. In fact, that's what we're going to call it, is we found it. And so what's true about E? There's a path to it. Exactly. So that's going to be one of our loop invariants, in fact, is that we know that found nodes, we're going to have a set of nodes that have been found. You see them. You know they exist. And how do you know they exist? Is, well, you walk the path to them. So they must be reachable from S, right? And what about D? There's something more special about D than E. Anybody see what's special about it? Right? What are we doing right now? Look at, what are we doing to D? Yeah. So I'm going to call D a handled node. What does it mean to be handled? It means that you have found all of its neighbors. All right? Everybody good with that? So that's going to be our definition, our loop invariant. Found nodes, you know there's a path from S. Handled nodes, you know all their neighbors are found. All right? And so that's, as I said, that's our loop invariant. And how do we maintain that loop invariant? Well, we're going to take some node that's found but not handled, right? And that's a good class of nodes. We're going to, in fact, put those into some sort of data structure, because those are the ones, what do we want to do, guys, who are found and not handled? We handle them, right? So C is found and not handled. And what do? We find its neighbors, right? So F is now found, right? We don't, here we found F, but it's been found before, right? So we don't have to say it's refound. We don't move it where it is in the data structure. We just sort of say, okay, it was found already, right? And so we find its neighbors. So how do we know we're maintaining this? Is that we're going to now call C handled, and all its neighbors are found, right? And how do we maintain the loop invariant? Well, this guy is found, and we know that there's a path to it from S. Are everybody good, this algorithm? There's our path, right? What's our measure of progress? Number of nodes that are... Right, so I've heard two answers out there. You could say it's the number of nodes that have been found, because we keep finding nodes. Is this a good measure of progress? What do we need as our measure? You need that every iteration you make progress, right? Are we guaranteed that every iteration we're going to find new nodes? No, you might not. So it's not a good measure because it might not increase. But what was our other option? I heard some people shout it, the number of handled nodes, right? Do we handle a new node every iteration? Yes. Listen to him. Why? That's what our iteration is. An iteration is take some node that's found and not handled and handle it. And it wasn't handled before, and it's now handled, so our progress went up. Right? So how do we start? We're standing on S, right? And what's handled and what's found? Nothing is handled, right? Nothing is handled because we haven't handled anything. Is anything found? S is found. Everybody else is not found and not handled, right? So, in fact, I have it up there. S is found and not handled. Other nodes aren't found. Right? Everybody good? And when do we exit? When all the nodes... do we exit when all the nodes are found? Yeah, exactly. We don't know. First off, we might not be able to... we might not find them all, right? And so we will never find them. And we want our exit. Remember, our exit condition has to relate also to our measures of progress, right? So you can't make any more progress. So actually, we don't know. That's one of our problems, is we don't know when we find everybody, or if we can find everybody. Can we find everybody that's findable? We don't know that. Have we handled everybody that's reached? We don't know that. But what do we do know is that we can make progress and maintain the loop invariant as long as there's somebody who's found and not handled. And soon as when can we not make progress anymore? We can't make progress anymore when found not handled is empty, right? When everybody that's been found has been handled, then we're stuck. What was your question? It's right up here. We're going to have data structures which are going to keep track of for each node. Is it found? Is it not found? Is it handled? Is it not handled? And the definition of found is, or the loop invariant, is anybody who you're saying is found, there's a path to it. And anybody that's you're saying is handled, you've found all its neighbors. Because in every iteration, we're guaranteed to handle a new node, but we're not guaranteed to find a new node. Right? What's the algorithm? Take some node that's found but not handled and handle it. Right? That makes the number of handles go up. But maybe this node doesn't have any outgoing edges. Or maybe all the outgoing edges are going to people who are already found. Right? So even though we're handling it, we're not finding anybody new. Right? And so in our algorithm, it grabs somebody who's found and not handled. Well, when everybody who is found is handled, then the set found not handled is empty, right? And then we're stuck. So that's what our exit condition is going to be. So here's the code. Do I go through it? No, it's up there. Right? So we have a graph. The input is a graph, which could be directed or undirected. And S is some node. And what are we supposed to do? Well, we start off saying nothing is found. And found, I don't know, put a little space there. Found not handled contains just S. Right? And what's our loop invariant? Our loop invariant is that the found nodes are reachable from S, and that the found ones are reachable from S, and the handled ones, their neighbors are found. Right? So and then what do? Is we exit when the found not handled is empty. Otherwise, we take U to be some node that's found and not handled. We take it out, found and not handled. And then we look at every V coming out of U, and we say, if V is not previously found, then we say, well, if it's not found, then it's obviously not handled, right? So we put it in found not handled. And then when we finish that, then we take U, it wasn't found not handled, we put it in found and handled. Right? Everybody follow that code? And when we exit, then the found guys hopefully is our answer. Right? Everybody got the algorithm? So what's left to be proved? Right? We've already proved that we can establish the loop invariant. We already proved that we can maintain the loop invariant. Right? What have we not done? One question is, does it terminate? And is this guaranteed to terminate? What is our measure of progress? The number of handled nodes, right? Number of handled nodes starts at 0 and goes up by 1 every iteration. Can it go up to infinity? No, there's only so many nodes in the graph, right? So we know it can't go up to infinity. So it's got to stop. Oh, well, that's what our goal is, to take somebody who's not handled and handle it. Right? So that makes the progress go up. Right? So here what we're saying is we got S starts to be found and not handled. So we find these guys. And now this is found and not handled. So we handle it. Right? All right, so back here, right, so now what we have to prove is the post condition. That's what we're missing, right? We have to prove that from the loop invariant and the exit condition and some little code at the bottom, we can get the post condition. Everybody agreeing with that? You remember? Oh, so let me state, if you should have all gotten an email from CrowdMark saying what your mark was. And some of you might not have gotten an email, and if you haven't gotten an email, then you should talk to me. And the various things that have happened, the TA said that there were 2 tests that somebody wrote but wasn't in the class list, so maybe they joined later or something, or maybe so if you're one of them, come talk to me. Another thing that has happened in the past, previous terms, is that you personally may have a number of email addresses, and CrowdMark mails it to one of your email addresses, and it might not be the email address that you look at. So I've always had 1 or 2 people, and then I find, oh no, it got sent to this email address, and then they go and look for it, and it's there. So that's another issue. All right, so what are we doing now? we're saying these are our loop invariants, right? Loop invariant says if it's found, then it's reachable from S. And if it's handled, then its neighbors are found. That's our loop invariant, right? And our exit condition says that all found nodes have been handled, right? And what's our post condition? There, I like that one. He said we visit every node, we found every node that we can. And what's the definition of can? It's reachable from S, right? The loop invariant we want is that all nodes U that are reachable by a path in G from S have been found, right? That found, in fact, we need that found equals the set of nodes that are reachable is going to equal the set of nodes that are found, right? So there's two issues here, right? The first node, so those are two issues, right? We need that found nodes are reachable, and we need to know that reachable nodes are found. So what about the first one? Can you prove to me, we assume the loop invariant is true. We assume the exit condition is true. Now, can you prove to me that found nodes are reachable from S? Yes. Yeah, if it doesn't have any neighbors, then all its neighbors are found. All right, so here, this is a case where I'm asking you a question that's so easy that you panic. I'm going to assume the loop invariant is true. How do you know that found nodes are reachable? That's the loop invariant, right? How do we know it's true? Is because the loop invariant tells us it's true. Right? Now, so here, now we need to prove that reachable nodes have been found. Yep. Well, edges can be pointing every which direction. There's not even a sense of direction. Every edge goes from some node to some node. And all we know is that we've followed this algorithm. Remember what the algorithm is. We start from S, and you keep handling nodes that haven't been handled. And then at some point, we know that the loop invariant is true, and we know the exit is true. I think your question is, well, if you found it, then if the algorithm found it, then we know that it's reachable. And if the algorithm, and then you handle it, and then it's handled. All right? So now we want to prove that if reachable nodes have all been found, right? So we do contrapositive, right? Everybody knows A implies B, means not B implies not A, right? So what does that give us? What's the contrapositive of this? Right, if it's not found, then it's not reachable. Not found, it's not reachable. All right, so we're going to prove that, and I call it the Great Wall of China proof, because, they have a Great Wall. All right, so here, we're going to put a big wall around, right? These are around the found nodes. And remember, we know that all found nodes are handled, so the set of found nodes equals the set of handled nodes, right? So those are the guys that are found. And these guys out here, they're not found, right? And so here what we're going to do is it possible have an edge that has its beginning in this set of found and not handled, and has its edge, and it goes to a node. It lets you out of the wall. Can you have such a node? No, you can't. Why? Because if this node here is in the set, then by the definition it's handled, right? And if it's handled, then we know all its neighbors are found. And so if this is a neighbor, it better be found, right? So from that loop invariant, it says you can't have such an edge. Right? Does that make sense? Yeah. Like, can there be such an edge? Proof by contradiction, there's an edge. Well, this guy's found and this one's not handled, so we're contradicting our loop invariant. Right? So, we could do more formal proofs, but the hand-waving proofs, you should all agree that if you start off in the circle, you can't leave the circle, right? There can't be. If it's not found, it's not reachable from S, because S is in the circle, right? And so you can't get out of the circle. Everybody buy that as a proof? So, hence, all reachable nodes have been found. And that is our entire algorithm. Right? Everybody good? So, let's give some thought to running time. The running time, you could say, well, what's their algorithm is every iteration you handle somebody new. Right? So the number of iterations is n, because we have n nodes. Each iteration you handle one of them. So is the running time n? Why is it not n? Well, we're going to handle one each time. And what's involved in handling a node? You have to find all its neighbors, and it may have a lot of neighbors, right? So the number of iterations is new, but is order n, but you might have lots of neighbors. And how many neighbors might you have? Well, you might have n neighbors, right? So then you could say this could be an n squared algorithm. But can we do better than that? What are we counting when we find our neighbors? Number of edges, right? Could it be fewer? Well, each edge is visited at most. If it's a directed edge, it's visited at most once. If it's an undirected edge, you might go in both directions, right? So, oops, where are we going here? Oh, we went way ahead. We went way, 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 way ahead. Let's start over here, guys. Well, let's just start at the beginning. All right. So each edge can be visited at most twice, so the running time is the number of edges, right? And that's actually good because the size of the input, right? How much space does it take to store the input in bits or something? Well, you got to store each edge, right? So the size of the input really is the number of edges. So that's why we say it's linear time. All right. So now what we haven't talked about is we have this data structure that holds our nodes that are found and not handled, right? And we take one of the nodes out of it. And so there's some choice as to which node. If there's more than one node in there, we have a choice, right? So we could be putting them as a queue, and in a queue, what you do is the new guy gets put in it, put at the end of the line, and the guy at the front of the line gets used first, right? So it handles the node that was found the longest ago, right? The oldest node. Or we could, right? And what's the advantage of grabbing the guy that's old is, well, if he was old, he was found earlier. And if he was why was he found earlier? well, maybe he's closer to S, right? In counting edges. We can do, and that algorithm gives you breadth first search. Then, and here's breadth first search, right? You start with S and you get to their neighbors and then their neighbors and their neighbors. You're kind of doing it one layer at a time. We could use a priority queue, and in a priority queue, remember it, every node has a priority. In this case, the priority will be, well, how close you are to S, right? So we have some sense of how close you are to S, and we'll grab the one who's closest, hopefully. And that gives us Dijkstra's shortest path algorithm. And then, or we could use a stack. What's a stack is you put the nodes on top, and you pop the guy who's been around the least length of time, right? And that gives you, he's the guy probably furthest from S, and that gives you depth first search. All right? So we will think about each